before going again, we'll take one more detour because we are on a hunt to understand loss functions. So we have to understand loss functions in machine learning. Okay, so basically what I'm trying to give you is, I'm not just trying to give you loss functions. Okay, this is a loss function, use it. I'm not trying to just say this is mean square error, you can use it. Rather, I'm showing you how to come up with loss functions. So I can give you some intuition behind, because now you know what information is. I'm giving you all the background necessary to come up with your own loss functions. If you understand these, but if you understand this information, and you can construct any sort of loss function on your own. Okay, that is the goal of these classes on deep learning. Otherwise, you could have just taken any deep learning course. So rather, I'm giving you formulation of what a loss function basically means. So loss function should somehow quantify. It should quantify how much off is your model. So if your model is trying to predict, say this g of x was the ground truth, and then we had this f of x, it was parameterized with these parameters theta, or we called them w in the previous session. So f of x comma y, so we said that there should be a function which we call a divergence function. So this function should somehow tell me how much off is this, and then we said that we can integrate between two functions. I made graph of some sort. I said, let's suppose this is the graph and this is the ground truth, and this is what we are predicting, and then we use integral. We said that we had problems in that, and then we resorted to this. We had to do this empirical risk minimization. Okay, everybody follows me till here? I'll write that empirical risk minimization formulation. What was that? Let me just write it exactly. So that was this. So you basically were computing expectation. You were saying that you have a probability distribution p of x comma y. Okay, so you have data points and the label. So you are sampling x and y from this. You are sampling x comma y from this, and now you are saying that we have a divergence function, expectation of this. So you are saying divergence function, and then you are taking this f of x and w comma y, because you are given outputs as well. Okay, and you are taking the expectation, and this we call as r of w. So this is r of w. So this over here was called our empirical risk or empirical error. So this was empirical error. What was the minimization? So you said r of w. This is, so you have to find optimal w, such w for which we'll get the minimal value, argmin of w. So what is the meaning of this argmin? Take such a value for which this expression becomes minimum. Okay, so this was our empirical risk minimization. We're dealing with this, and basically we were trying to come up with this divergence function, such a function, so that we'll have to minimize that. It should somehow quantify. It should give us a number, one number. So usually we call this a loss function, cost function, or these things. We name it differently. Okay, let's again take one more detour to understand this. So information theory is over. Let me just before coming to this loss function, we should also know like the output functions that we use in the neural networks. Okay, just before the loss function. Okay, if you remember a neural network. So neural network was something of this sort. So you had an input layer. Okay, and then you have some hidden layers in between, something of this sort. You had hidden layers, a lot of them. So these were our hidden layers, and then you had output layers. You had, let's consider this to be output layer. So these were our output layers, which was giving you the output. Okay, and now if you see, we also used activation functions. We use what's called as first we used linear transformation, so which was called as affine transformation or linear transformation. Affine was a better word to use for that, because linear transformation is also an affine transformation. So we made a neuron like this. We said initially we do aggregation, that was called as affine transformation. So we performed affine transformation, and on the second we used activation function. So why did we use activation function? Because if we do not use activation function, your network is nothing better than a linear classifier. It will not do anything but just linear classification if you do not use an activation function. Activation function is what makes it non-linear. Okay, and we saw that if you just use one perceptron, and if you do not use this, you can just come up with the linear distant boundary. Even with the ML multilayer perceptrons, if you do not have activation function, it will be nothing but a bunch of neurons making a linear decision boundary. What is the meaning of linear? You people are well versed with that. Okay, and this activation function is non-linear. Okay, and this affine transformation, it's linear transformation. So why is it called affine? I told you that if you add that by, so you are shifting you're shifting it from the origin. That's why it's called affine. So now you see this activation functions that we were using. We're using sigmoid functions. We can use ReLU functions. We'll have a detailed discussion on this as well. We'll have a lot of discussion on activation functions. There are at least tens of functions which I know of. What activation functions can be used, and they have a lot of impact on how neural networks will learn. Okay, how efficient it will learn. that we established. If you just have one non-linear activation function representing the power of neural networks, that we all learned. It can learn any function. It can approximate any function. But how efficiently it will learn depends on this activation function as well. So affine transformation is good enough. You are just aggregating it somehow, and then you are applying some non-linearity, some activation function on that. So we'll have a separate discussion. We'll mark it with star. Right now we are having this discussion because last layer activation function. If you see this last layer, if you let's suppose have this is the last layer or the output layer. If you use the same activation function, let's suppose whatever we used, if we are using softmax everywhere, and if we use softmax here also, so because you know that softmax value is between 0 to 1, so the value of softmax lies between 0 to 1. Sometimes we might have a problem that we are expecting a problem where the values, the output values are 2000, 5000. It's some continuous problem. But if you also apply the same activation function on the last output layer, the problem will be that you would not get always, you will not get the numbers that you want. Okay, that is the problem if you use the same activation number. First we'll see the problem. Why are we using different activation? Why to use different activation? Different output activation. The reason I told you that, if you have solving a problem where you don't need just the value between 0 and 1, because if you keep on applying this sigmoid value, you will see that they somehow taper off the values somehow. If you would sigmoid, so you will get values between 0 and 1, but sometimes you want the output values to be 2000, 5000, 6000, something of that sort. So we should not then use the normal activation functions that we used in the hidden layer. Okay, and in terms of let's suppose classification, you can still adapt these, but somehow you should use some different activation function for the output, so as to do whatever is expected from the network. So you are making a network of this sort, so whatever you are expecting at the output, you should accordingly choose the activation function. So how to choose the activation function is basically, so whatever problem you are solving. So I'll just write one line. So why, I think I answered the why part, and now what to choose. Okay, do not consider that we'll be done with activations here. I'm just speaking about the output activation functions. We'll take maybe separate 2-3 lectures on activation functions. So what to choose depends on the problem. It depends on the problem. Many other problems are regression problems, some are classification problems, there are special cases as well. So without an output function, the network will just produce the raw output, which are called as logits. Okay, so raw outputs from network, they are called as logits. Okay, many of you will also see PyTorch code written that you will see I'm applying this to logit. So whatever you get here, so when you aggregate it till here, so whatever you are getting at this point, what I'm marking over here, because you are not applying activation on the output, you are calling that as logit. So that is the raw output. Okay, you are calling that as logit. So logit is basically what we have before we apply the output activation function. That's the logit. So now we'll have to do something, because depending on task, we'll have to somehow convert these logits. So these logits should be converted to something which we can perceive, which we can make sense of. Suppose if it is a regression problem, say if it's a regression problem. So what is the meaning of regression problem? If you can take any continuous filings. Okay, so what we can do is we can just use logits as it is. We cannot use any activation function, suppose. Okay, so but let's suppose if it gives values 2000 initially, but you know that by the help of loss function and by the help of adjusting those weights and biases, it will adjust itself. So it's in terms of regression. Or you can use something which will, maybe if you have to get values between say 100 to 200, you can use something in which you will get values in this range. So for the regression problem, let's suppose if you have a classification problem. Say if you have a classification problem. So what you usually can do is you might want probability between 0 and 1. Okay, so as I said in the regression, the last thing will be you'll just take W transpose X plus B. You will not do anything. You will say as it is, because it will give you answers from -infinity to infinity. So that's what the value of S is. Regression targets are usually unbounded because you don't have to bound them. So now if you, let's suppose, are doing classification tasks, so what you can do is you can use a sigmoid. Okay, you can use sigmoid in this because it will restrict the values between 0 to 1. So you can say 1 divided by 1 plus e to the power minus z. So whatever you got values earlier, so you'll apply this. So say you are saying probability of y given the point x, something of this. A probability of class 1 given probability is this. So you'll compute it after this. So you'll say probability of y is equal to 0, the class label is 0 given this probability x. So you will at the end apply some sort of sigmoid. So it will give you value between 0 to 1. Say this is 0.5, so and this probability is 0.8. So whichever is higher, you will assign that to probability. So but you are using some other activation function. Okay, so this is with respect to the binary classification. So now if you have multi-classification problem, okay, if you have multi-class classification, now here you can say just two, here are two classes and I just predict the probability. So now if we have this multi-class classification, so what you can do is basically, because you will have to now have, let's suppose 10 classes, you have some 10 classes, you can have some probability over here, and then you can directly convert this into probability distribution. So you are given the value, say we have some 10 classes, so we'll have output 10 neurons at the output layer. So now you will get some values in there, you will get values 200, 500, logits basically, some 100, some 30, something of this sort. Now you will have to choose one class among them. So what you can do is you can convert whole of this into probability distribution, not individually. So what you can do is you can apply a function on this which is called a softmax, which we'll briefly see. So you can apply softmax function on this. So what softmax function does, it will take all these neurons, it will take all these logits, okay, and it will convert them into probabilities. Okay, not just individually. If you see the difference, so in this case when we were applying sigmoid, so sigmoid was applied per neuron, okay, and it was giving per neuron value from 0 to 1 and 0 to 1. But if you sum up all the probabilities, that can be greater than 1, because probability is between 0 to 1 for individual neurons. But when you are applying this softmax, you are applying it on the whole output layer. So output layer in this case, if it contains 10 neurons. So but if you now apply the softmax function on that, you will get certain probabilities on these. But if you sum them all these up, so if you sum probabilities, if you sum all these probabilities, so you will get probability is equal to 1. Okay. So all of this will be given probability greater than or equal to 0. But when you sum all of these things up together, you will get one probability. Okay. And then whatever is the highest probability, so in turn, you actually wanted something of this sort. So let's suppose you have a random variable x, the multi-class classification problem, where you are classifying images. You are classifying cat, you are classifying dogs, you are classifying lions, you are classifying bears, something of this sort. Say these are the 4 classes we have. So this is the random variable. So now once you get this, so each of the neurons is responsible for predicting so what the output should be. So now on applying this softmax, so we'll get some probability distribution. Suppose you got the probability distribution 0.2, 0.4, 0.15, maybe 0.25. I think this is equal to 1. Now the class, the label actually was, say it was a cat. Suppose that was a cat. So what you ideally wanted is something of this sort: 1, 0, 0 and 0. So this is the distribution that you wanted. But your network predicted something of this sort. It said that this cat with a probability of 0.2. But if you sum all of these things up, so this will be equal to 1. So now this encoding is called as one hot encoding, because it's 1 at the class that we want, and rest at the rest place it is 0, and we can compare this. So we ideally wanted this, but network actually predicted a distribution. So usually in multi-class classification case, you will get a distribution. You will want to get a distribution. So that is why you apply the softmax function. So what is the softmax function? If you see, so you will take all of these VAEs. So you have y1, y2, y3, y4, something of this sort. You have these 4, say you have this 1, 2, 3 and 4 outputs, 4 output neurons. Consider this as y1, y2, y3 and y4. Now this is prediction. We can put a hat on this so that it is clearly mentioned this is predicted wise. Now what you can do is you can apply softmax on this. How? You can say yi, this is equal to, you will take first the exponent of this, e to the power zi. Okay, because you know this, how did we get this yi? Okay, because it will get this from zi's. Okay, after this what you can do is e to the power zi, whatever you got zi from here. So you are getting yi from that. So you take an exponent of this and you take exponent of all of these also. So this is e to the power zi, I goes from 1 to 4. You sum up all the values over here and then you take an exponent of this, okay, and you will get a probability distribution. You can directly take sum, but the sum had the problem. So let's suppose if you have values 10, 20, 30 and 40. If you want to convert this into probability distribution, you can sum all of these up. So this will be 70, this will be 100, I think. So the total sum is 100. So you can divide everything by 100. So you will get 10 divided by 100. So you will get 0.1, 0.1, 0.2, 0.3 and 0.4. This is now a probability distribution. But why don't you use sum? Because as we know that we want a differentiable function and it should be somehow smooth. So this function is that. Let's have some discussion on this softmax function for a while, so you understand this. So this function over here that I defined is called as softmax. So you'll take all the values. Okay, you'll first take exponent of these zi's and then you'll sum them up. So this is the summation part. This is the normalizing factor. So you basically want normalization. So this is normalizing factor and then you want to normalize each of the values. So you're taking value for this you are taking it to the exponent, and then you are dividing that with the normalizing factor, and you are getting values between 0 to 1, that this value will be always greater or equal to 0, and the summation of all of this will be equal to 1 after you apply this. So summation of VAEs, predicted VAEs, after applying softmax. So I goes from 1 to, let's say in this case 4 in general n. So this will be equal to when? After the softmax function is applied. Let's consider this softmax as s. So s of this. So s of z is equal to yi. So s of zi. So you know that s of zi is equal to yi hat, and here s is equal to softmax. And we get the definition of softmax over here. Okay, let me just share a graph with you so that you can visualize this function. Give me maybe a second or so. So this is softmax. So if you see, I have 4 values in there. First I'll explain this graph. So you have this a red, okay, and then you have this b orange, c green, and then you have this d value, that is blue, and then you have shift s, and then you have multiplication v. So if you see, these are the 4 values. Consider that random variable we to cats, dogs and stuff like that. So these are the 4 values which we take. Okay, this. So if we now take this value, let me just remove this because we are taking it to e to the power. So this is the e to the power x function. I should not use this multiplication. Give me a second. I'll fix it somewhere. Now if you see these values, so these are the values in the graph. So one value is shown over here. So this is the value, if you can see my arrow. So these are the 4 values. So they are having different values. So I can take values like this also. So I can shift these values. Okay, now I am making the value so that it is easy to visualize. This is the value, and then I am taking a little bit greater value for this b, and a little greater value for c, and d a little bit greater, or something of this sort. So if you see, these are the values. This is a, this is point b, this is c, and this is d. If I again zoom it, so these are the values a, b, c, and d. So I am parallelly showing the graphs as well. Now if I apply e to the power x on this, so this is the function e to the power x. If you see, this function over here is e to the power x, the function over here. And now if I just take these values, so these are the base values, and now if I exponent them, so you will get these values. So this is e to the power x. So for this value, this is e to the power x. If I again go back, so this is e to the power x. And now you can clearly see over here also. Now what I am doing is, I'll have to apply softmax on these functions. So what softmax will do is, it will compress this. So if you see the below graph, okay, below graph, if you see, so it is taking these values. The sum of all these values is summing up to 1. Okay, so this is the unsquashed graph, if you see this, and this is the squashed graph. So in below, because we are squashing it. Okay, if we can remove this, you can clearly see all these values are there. So now below part is when you apply the sigmoid function. Okay, this is the squashed bar graph, and this is unsquashed graph. So above is the unsquashed graph, where we have, and below basically is when you apply the softmax. So here you are applying the softmax. So above part is the logits. We can consider this as logits. So let me write it. So these are the logits, the outputs that we get directly. So these are the logits. And when we apply this, so when you apply softmax on these, so what you can do is you will get this. So we can call this as logits, and you can call this as output. So these are the real outputs then we have. So if you see this, these values, now you can see the all the bars when added, so they add up to 1. So if you see the value over here, they add up to 1, and they have different. If I change this, you will see the graph also gets changed over here, but this will not get changed. Here the proportion will get changed, depends on the values of these a, b, c, and d, the different 4 classes. You can see the proportions are getting changed. I can change them here and there. You are seeing the proportion is getting changed, but all over the total is equal to 1, because it's a probability distribution. So the total probability will be 1 for these are 4 events. So you have these 4 events, and that this is unsquashed one, the logits we are having, and then we initially apply e to the power x. So initially e to the power x was this. So when you apply this softmax, you will see this. You will see this over here, and this is how it will behave. And this each of the value is normalized value. So this is e to the power x divided by normalized constant. E to the power x divided by the normalization, divided by sum of all e to the power x. And then this is the total distribution that you can see over here, and this is the bar graph of this. So how many of you got the softmax function? Pretty standard stuff. So why is the softmax important? So if you see, we'll use it for many problems. They might not seem classification problem, but we'll use softmax there. How? Let's suppose you are building a language model. So language model is nothing but a next word prediction machine. So you have some context, and then you have to predict what comes after this context. Let's suppose cat sat on the dash. Okay, this is the context. So if you see for our language model, this is the context. And now over here, this is the next word that we want to predict based on this context. So how to predict this? So now what you have is, in the language models you have vocabulary. Vocabulary basically means the number of tokens you have, total tokens. So total tokens you can have there. Let's suppose this is a word level tokenizer. If you have words, so you'll have whole of this dictionary basically. So you'll have all the words that are there in English. So suppose there are some 1 million words in English. So you will have this dimensional vocabulary. So this is the vocabulary size. So what you want to give is, you want to give each of them a probability. Okay, how much given this context, probability of next word given the context. So if I am given this context, what is the probability of next word? Let's suppose here the word starts with a, then starts with AB, then starts with apple, and then all of these words. So all of this will be converted into probability distribution. So if you see these language models, at the output, the output layer basically will consist of this. So there will be a network which will have the outputs equal to number of the number of tokens in the vocabulary is equal to the number of output neurons. So what will you give there is, so initially you will get some random values, 100, 200, 500. So you will apply softmax on this. Once you apply softmax, so after you apply the softmax, what will you get is, you will basically get a probability distribution. You will get some 0.001, you will get some 0.2, 0.00 something for all these words. Okay, then the strategy comes into picture, which one to sample. So top K, so usually top K sampling is done. You can be greedy, you can just take one of them. Okay, you can take let's suppose the topmost, which has the highest probability of that. So you will sort them based on the probability, and you will say this is the next. The cat sat on the mat. Okay, now one more thing over there. So we can throw one more value which is called temperature. So you can just modify this softmax function which is called as temperature. So we can modify it like this. I'll take your question, just hold on for a second. This yi hat is equal to e to the power, because you did zi, so you can divide it by t. So this factor is called temperature. Divide by summation of I goes from 1 to n, whatever number of logits are there, then e to the power zi, or you should use j here because you should not overload the symbols. J goes from 1, j divided by t, and this little number over here is called temperature. So it tells your model how much creative to be. So if you set the temperature to be highest, it will be more creative basically. It will give it will not distribute so such. You can check with this. I can show you the graph that this temperature has an effect. If you keep this temperature, let's suppose this t is equal to 1, this becomes like softmax. Okay, so if you decrease the value, it will become more creative. It will shuffle the probability here and there, but still this will have all the properties of the softmax function. That is, it will be between giving value 0 to 1. But this temperature, one more term, if it's equal to 1, you will basically want it to be like softmax, exactly behave like softmax. But if you just throw some temperature, so when you have this value t, you can give it value from, let's suppose, greater than 0, because if in the division you should not do division by 0. So, and you can give it between 1, or you can give it more value as well. Okay, so as to control this factor all over. So that's why if you see language models, if you have seen some playground or ChatGPT, if you have seen some Google development, that there you can set the temperature. So this basically is having some control on these things. So it is basically controlling the probabilities that it can give to the last logits, and it's converting them into, it is giving some other distribution, but still that distribution is controlled with t, so that how much creative a model can be. I think we have a question, then we can start from here. Yes. So that's how temperature is. So usually this temperature you will see this temperature in language models, or maybe some other cases also where this temperature sort of controls creativity, what I can call as creativity, loosely speaking. So it controls creativity. So this is the softmax version of softmax that is the less common function that we generally use. Okay, so we can also use what are called as soft plus functions. You can use ReLU, soft plus, exponential, a lot of other functions in the output. But I wanted you to understand about softmax. I think that is clear now. Okay, the softmax function is going to be a very important function, which we usually use in terms of the distribution, because we are talking about distributions P and Q. So this is our distribution. Let's suppose the ground reality is some one hot encoding, something of this sort, which we earlier wrote, that you have the image of cat, and this is the actual distribution that you want. But whenever you run the network, it will give you a probability distribution. It will give you 0.2, 0.3, 0.4, something of this sort, so, and 0.1. Okay, but you wanted the whole mass to be concentrated on cat. Okay, and now you can you have two probability distributions, P and Q. Okay, this is the ground reality. Okay, and this is the predicted one. And then now we can have discussion on this divergence. Consider you have this Q. This is the ground reality G of x, and this is what model predicted. Okay, now we'll have to apply this divergence function on this. Okay, and then we'll have to compute basically the expectation of this, and we'll have discussion on divergence next. Any questions still here? Because we wanted to understand this divergence function. If you see, okay, the first thing that we saw is we read about some information theory, we read about some output, how output functions can be. The one concept that you will see always coming in this divergence function is cross entropy. So we'll first see what cross entropy is, and then we'll see what cross entropy loss is. Okay, now if you have two probability distribution, P of x and Q of x, these are two probability distributions. In our case, you had some ground reality and you had what the model predicted. You have what the model predictions are and the ground reality. So these are two probability distributions. As I said, there's one will be a one hot encoding vector, because you will have all the probability mass concentrated on one class, because it's a multi-class classification problem. And then other model prediction will be usually a probability distribution. So consider this to be a true probability distribution for outcome xi, and this is the model prediction qi. So this is our model prediction. This is model prediction. And this is the true probability distribution. True distribution. This is model prediction distribution. And now you know that what is the code length. So if I apply log of, say, I'll apply log of qi. Log of q of qi. So this will be code length, basically information content in this. So information content. Let me again see if I'm choosing this as right. So P of x is the true probability, and Q of x is the model predicted, and this log of Q of x is the information content based on what model is predicting. Okay, so now what you can do is, usually you had entropy. Entropy was like this. So you had, let's say, P of xi. If I used for this model, what is the entropy of this model? You can say Q of xi minus say log of Q of xi. So this will be called as entropy of the model. 1 from 1 to n, say suppose this. So this is the entropy. But what you can do is, if you, because for each points you will know this probability, because you have the sample, and you can just say this is the one hot encoded vector. So somehow you can just unveil for that particular point what is the true label for that. So you can replace this with pi. So if I say P of xi, so now you see that we are having two probabilities. So this is the original one, you had original entropy. So if I just showed the qi, but in this case I use pi, so I use cross entropy. So I use this probability what actually it should have been. Then I use information content predicted by the model. So this is information content by the model, but you are multiplying it the expectation. You are saying that probability I am taking is from the actual probability distribution. So you are crossing it. You are taking one term from this and one term from this. So somehow this is crossing in a way. So but still you are computing the entropy. So this is called as cross entropy. Okay, so what is basically cross entropy saying is, so you can start from a distribution P. So you can just say what is the minimum expected code length. Okay, if you have actual entropy, so it is minimum expected code length, or minimum. I can say that what is the information content in that, but you know that this generally gives the minimum. When you compute the entropy, so this will give you the minimum number of this. So when you compute this cross entropy, so what cross entropy basically is telling you, so it is telling you now you are not computing it based on the original distribution, or you are not having the same distribution in both things. So you are taking one actual distribution and you are taking one what is predicted by the model. So you are saying that if I use models modeling, if I use, because I said that this is called as encoding. So if I use models encoding, if I use encoding from the model, see it from the information theoretic perspective. If I use encoding from the model, my model is just an encoder. Okay, so how much information content is there then? So basically it will tell you how many bits to use. So if the model is very close to the actual thing, so this is the encoding scheme. So I am using model as an encoder, and it will predict me number of bits. It will tell me number of bits that are used. And if I had actual probability, the real probability, the least encoding, if I had the access to the actual data, all the actual data, so I would get the least number of bits. But you know that model will be somehow off. So you know that this value, if it is greater, if this value is a lot more, so that means you are not getting the optimal code length. Okay, that means model is off by something. Okay, if you are getting the least one, if you actually had this, if you have access to P of xi and you computed log of xi, but this log, if you actually had the probability, so you will get the least value. You will compute the least value, I is equal to 1 to n, and you will have the minimum code length. But you know that you do not have access to the probability distribution. Actually, all you have is basically a sample. So you will use this from the model, and you will use this from the sample, whatever you have. Okay, you are saying based on if I use this model, how much discrepancy is there, how much off my model is. So this is somehow, if this is more, if this is not optimal, if this is more, so this will tell you the higher value of this will tell you that model has more error, model has more problems, more error. That's why we use cross entropy. Why? Because if you had the real probability distributions with you, you could have used the entropy. Entropy will give you the least number of bits, but you know that now I am not having the real probability. All that I have is model. So I'll use model, and for that particular point, I'll use what is its real value, and I'll compute the cross entropy of that, not the exact entropy. So the cross entropy, if it is higher value, that means model is not optimal. So it's not giving me the optimal code length. Rather, what is it giving me? It is giving me a little higher than that. Okay, I can give you examples as well. Let's consider this. If P is equal to Q, if probability of P is equal to Q, then you know that cross entropy is equal to the entropy. Okay, so with that, it's basically a perfect match. Say P is equal to 0.8, 0.2, and Q will also be equal to this, because we are taking perfect match. So if you now compute this, the minimal number of nats will be 0.5004. So this is the information content, that average information content. So cross entropy is equal to entropy here. So this is the minimum. This is the encoding cost. Okay, so this is the minimum number of bits of or nats if I use natural log. So this is the minimum number of nats that I will use to transmit the information. Suppose if there is a mismatch, I have probability P which is 0.5, 0.3, 0.2, and I have probability Q. So this is my actual distribution and this is my predicted one. So I am predicting something of this sort, 0.4, 0.4, 0.2. It is off by little. But if you compute this, if you compute H of P, Q, so this is cross entropy. This is cross entropy. Okay, so if you compute this, so this comes out to be 1.0549. Okay, these many nats. So cross entropy is this much. So optimal value was this. Optimal value was 0.5004, but you are getting 1.5049. This. So you can see that this is higher value. That means the model is not better. You can see that there is some mismatch. So this should have been 0.5. This is 0.4. This should have been 0.3. This is 0.4. And this one is correct, but you still can see that model is off by a bit. If model is off, it is shown by the information content. So you are using encoding scheme from the model, and you are using the probability distribution, actual probability distribution, what you can observe in the sample. Then you can see that you have greater number of nats. So if you have H of P, this is called as entropy. Okay, H of P, Q is called as cross entropy. Now you can see if you say H of P, Q, and if you take cross entropy and you subtract entropy from it, so this is called as KL divergence. So how many of you are seeing it for the first time? This is KL divergence. So basically what KL divergence gives you, how much off are you? Okay, cross entropy can be directly used, you can still use KL divergence. So if you remember, we were discussing about entropy. We went to entropy, then we went to cross entropy, and then we started introducing KL divergence. Okay, I said what is cross entropy now. So if you are using one distribution, that is the model's distribution or predicted distribution by the model, and then you are using the ground reality and you're computing entropy based on that. So that's called as cross entropy. Okay, so this is the real distribution that you have, and this is the model's prediction. If you use this, this is called as cross entropy. So why was this useful? Because you are now trying to model, you're trying to come up with a coding scheme, optimal code by using the model, and there is some real truth, there is some actual distribution. So if this model distribution, if this prediction by the model is not good, so you will have this deviation, you will have this divergence, this metric, which is called as cross entropy. You will have this more. So if this is more, then you will not have it as the optimal code. So if this is optimal code, then you will say that this is equal to entropy. So if that is equal to entropy, the difference between entropy and cross entropy will give you the KL divergence. That is what is written over here. So this over here is cross entropy. I'll write CE, and this is entropy. Okay, so this is what is given by KL divergence. So there we took some examples also. Let's take some catastrophic case. Okay, let's suppose if some probability distribution P is equal to 0,1. So this is the probability distribution, and your predicted model predicted this. So it did a catastrophe. So it's almost opposite what it should have predicted. Okay, now you have to compute the cross entropy of the system. So what is cross entropy equal to? So you'll use summation of I goes from 1 to 2 in this case, negative of. So this is probability x takes value xi log of, let's suppose some probability is q of x takes value xi, something of this sort. So now if you see this, so in this case it should be, the answer will be 1 of if I use natural log instead of this log to the base e, so I'll get something of this sort. So if you evaluate this, so this will tend to infinity. Okay, because log 0 is infinity, multiply 1, this is infinity, and this quantity will be equal to 0. So when there is this catastrophic result, this is opposite results, whatever we wanted. If the distribution that we had is this, so this P is our ground distribution or the ground truth, and this is our prediction by the model. So when we use the cross entropy, you saw that it went to infinity. So it said that you are infinitely wrong. Okay, what is now cross entropy giving you? So it is giving you, like, based on this, if you are constructing your optimal code by using the model for the distribution, that is the real distribution. If there is some discrepancy, so that model will show you. So I said that. So KL divergence can be now seen like this. So how much is now that? If you want to quantify that, you can quantify that by KL divergence. So this cross entropy will only give you it will give you basically the number. Okay, you are off, but how much off are you? So you can compute that by using KL divergence. So KL divergence will be effectively equal to, so if you have this cross entropy and you subtract entropy from it. So this is basically telling you number of additional bits, number of additional bits used for encoding when the coding scheme used was from the model. Used was from the model. So this is what you should remember. So that's how these two things are related. So you had cross entropy. So this is your cross entropy, and this is your entropy. So when you subtract these two things, so what you will get, you will basically get the additional number of bits. So this is your optimal code if you had the actual distribution with you. So this is what optimal scheme is. This will give you the minimum number of bits, the minimum number of bits that you should have to encode the information or to transmit the information. Now this will be some additional thing. So this will be your cross entropy number of bits. Maybe it should be more. It will be more than this optimal. So when you subtract these two things, so what you will get the additional number of bits that you have to use in case you use this this model. You use basically the predicted the model by the neural network, and you are predicting that for the real for some real distribution. So you will get this. You will get the number of additional bits in that. Okay, this will tell you the discrepancy. So this whole thing will tell you the discrepancy, or this will tell you the difference between these two distributions. So this is called as KL divergence in terms of entropy. Everybody clear on this point? So three questions are addressed. The first question we addressed yesterday was that why do we apply the softmax if you had softmax? Because as I said that if you use softmax, you are converting all these things into probability, and now suddenly what will happen is that all the theory that has been developed by probability, the framework of probability, will apply to these problems. Okay, so because that's why you apply softmax on this. So now you convert that output, you convert those outputs into probability distribution. So whatever you know about probability suddenly applies to that. And in this case, because this cross entropy, if you see, it is from information theory and then probability. And now if you apply softmax in the last layer, so you can now use cross entropy, because this cross entropy, its roots are in probability and information theory. Okay, second question is, what is the second question? If somebody can remind me, second question by Muzaffar again. Okay, and why do we use like different versions of these things? You can still use, because sometimes computationally one thing is easier to calculate. As I said, you usually will resort to log functions. Why? Because if you can see, if you perform multiplications in computers, let's suppose you have two numbers P, Q, and maybe more than two numbers P, Q, R, something of that sort. So if these numbers, let's suppose big, so let's suppose they are 10 to the power 5, 10 to the power 6. If you keep on doing that, you know that we have finite memory to store these things. So what will happen? So you will have a problem of overflow. So if these numbers are too small, let's suppose they are around 0. So let's suppose this is 10 to the power minus 4. This is 10 to the power minus 10, something of this sort. So these numbers are too small. So what will happen? So in this case, overflow might happen because of finite memory. In this case, underflow might happen because we have finite memory, and due to precision errors, we will have this floating point funkiness. So because of this, if we use log, because you know properties of log. So properties of log is that if you have multiplication, so if you apply log on multiplication, what will happen? So you can convert that multiplication into addition. So you can now store these results more precisely. That's why computationally these things are feasible. That's why you will majority time see that there is some log involved in the loss function. And all these functions, let's suppose this cross entropy function or the functions that we saw earlier, softmax, when we apply those functions, because we have to somehow minimize things, we have to find optimal points. So for that we should have differentiability. Okay, so one reason I gave earlier is that So when we convert things into probability, so framework of probability comes into picture. And second important thing is differentiability. So if a function is differentiable, so you can apply calculus on that then. So you can differentiate the function and then you can find the optimal points. Okay. So because since cross entropy is differentiable, so it works very well with gradient descent optimization methods, or maybe some other modifications of gradient descent. Okay. It makes them suitable for these neural networks. I hope that I answered the question. So one more question was in this catastrophic case. So this is the catastrophe. So if I have the probability distribution, which is 0, 1, and then Q is almost opposite, not the almost exactly opposite of this. So the answer was infinity. So the analogy I gave, this is the worst case scenario. So if the probability was, predicted probability was, let's suppose 0.99 and here it was 0.1, still it can be more wrong. So in this case it is wrong, but it's not infinitely wrong. So what is infinity wrong? Basically the worst wrong that you can get. This is the worst wrong. You cannot do worse than this. You cannot do better than this also. So if you have 0 and 1, though, this is the best possible scenario. So what is the worst possible scenario? You do almost opposite of what is given. So because this cross entropy is telling you how much wrong are you. So in this case, it is telling you that you are infinitely wrong. You cannot do worse than this. Okay. These were the questions which were asked. Let's see different versions of this cross entropy that are used in deep learning. Okay. We'll just write the formulation first, and then we'll do some probabilistic treatment afterwards to reach those conclusions again. Okay. One function that you'll use in terms of classification, if you have classification problem. So what is classification problem? So because you know that many of these real world problems, if you have to consider something, some problem where you have two classes, okay, that's binary classification, and you can have multi-class classification problem. Let's first see binary classification. So binary classification. I can also write it mathematically what a classification problem is. So whatever labels you have, they belong to, these labels can take values 0, 1 till some k. They can take some discrete values in the classes. And now binary classifications is where you can take two values, 0 or 1, and multi-class classification is where you can take 0 to k. Some k classes are there. So this is multi-class classification. Okay, now you might have heard about two types of cross entropy. So first cross entropy that you will be seeing is associated with this binary class classification. So in that you have binary cross entropy, BCE. You might have heard this short form a lot. So this is binary cross entropy. So now you know that how entropy is defined. So in this case, I have two values. In the binary classification case, there are two classes possible. If we can take a real world example, you can have an example of two types of emails, spam emails and non-spam emails. And then you can have, let's suppose, happy, sad, some emotional classification. You can have whether a person will buy the product or not, should I recommend the video or not. There will be a lot of problems which will for which we can use this binary classification, which will have two classes. So now in that case we'll use binary classification. So now you know that we have only two classes in this, 0 or 1. So how can you modify this loss function, the generic loss function that we had? So you can say that we have this loss function L. You can use negative of y log of prediction and then plus 1 minus y log of 1 minus y bar. So this over here is your binary cross entropy loss, BCE, which you generally use if you have coded in Python or something. Directly you can use this binary cross entropy like this. So what is it doing? So this y over here is the actual thing, the ground truth, the actual value that the data point had. This y hat is the prediction. Okay, now what you can do is you can be either wrong or right. So there are four possibilities. So you can have something of this sort. So you will have 0. So let's suppose your base truth is, your base is 0 or 1. This is the ground truth. I can write it GT. GT means ground truth. So prediction I can write it with PT. So the prediction could be 0 and it could be this is 1 for this. So this is when the classification is right, when you do not have an error. A ground truth could be 0 and 1. So you could have misclassification. These are the four possibilities. Okay, so this is my ground truth. So ground truth is 0 and the prediction is also 0. So you are right. So in this case, this is correctly classified. So again, in this case, 1 and 1 correctly classified. Now you can have misclassifications. So if you can compute this loss in terms of all these cases. Suppose you are using the first case because you are having y and y this, because if you have, so if you see this now, so this will handle one class and this will handle another class. Why am I writing y and 1 minus y? Because it's in terms of probability. So if one has probability y, other will have probability 1 minus y, because sum should be 1. Similar case with this is y and this is 1 minus y prime. So if you have one neuron, let's suppose at the end of the network, so if it gives you the probability of 0.4, so if you consider this 0.4 is the probability of event happening, probability of A is equal to 0.4. Probability of, let's suppose if there are only two events and either of two events will happen, either event A will happen or event B will happen, so automatically you will say that probability of B is equal to 1 minus 0.4, that is 0.6. So this is the case in this case. So you have two classes, either one or 0. So one of the two will happen, either it will be 0 or it will be 1. So if you are giving probability y to one class, then you will give probability 1 minus y to other class. Now if you use these four things, the things that I wrote here, let's suppose you will use right predictions for the first case. So ground truth, suppose ground truth was 0 in this case. So let's suppose if you take this 0 and y prime was also 0. So this will handle the zeroth class or 0 class. Oops. So if you take 0 class, this will be handled by that. Why? Because if it is 0, so let's suppose if it is 0, so this will become this will vanish. So this over here will vanish, because anything multiplied with 0 will become 0. So if it is 0, so this will be going to this case, and then we'll rather shift on this. So anything that is now predicted will be based on this. So we'll take the first case. So for 0, so this will be vanished, this one, and we'll move to this class then. Okay, let's suppose if now you give value 0 over there here, if you give value 0 over here, if this y was, suppose if you consider this case now, if this y was 0 over here, so this will become 1. Okay, so this is rather reverse. So this class is specifically for 0 and other is for 1. So this is for 1 class, because 1 is when this is making the whole thing 0. So if you are considering 0 now, so see this, so this class, this term will be vanished if you have ground truth is 0. Suppose the ground truth is 0. Okay, and this will be vanished. We are left with this term. So 1 minus 0 is 1. Okay, now log of 1 minus y prediction. So if the prediction was also good, see over here, if the prediction was good, that means it can be prediction is 1, that is prediction is right. Suppose so prediction is 0 in this case, so then it will be log of 1. Okay, you can clearly see over here. So you will have loss of 0. So log of 1 is 0. So in terms of prediction is right, when you are using 0 class over here and the prediction is also 0 over here, so you'll be left with 1 log 1. So 1 log 1 basically is 0, and this term was vanished. So loss is equal to 0. So you are correct in this case. Okay, so the first term 0. Let's suppose if you are wrong. Suppose if you are wrong in this case. So the ground reality was 0. So ground reality was this. But what happened? You did misclassification. You said it is 1. So this will again go to infinity. So this is log of 1 minus 1. That is log of 0. This will go to infinity. You are wrong. Entirely wrong. Okay. So if you see this term. So this term handles the 0 class. So by the meaning of 0 class, I mean that if the ground reality is 0, if the ground truth is 0, so that this is handled by that. Now if you see 1, okay, so if you have class 1, so this will 1 minus 1 will be equal to 0, so this term will be vanished. Now we'll go to this. If you have this 1 1, that is the prediction is right and the ground reality and the prediction is same. So what you can do is, if y is equal to 1, so you'll have y is equal to 1. Now log of 1 is also equal to 0, so loss will be 0. Okay, if it is reversed now, if it's a misclassification case, this case misclassification 1 and 0, the ground reality was 1, but the prediction was 0. Now we can see that y is equal to 1, log of 0 is infinity. Again, the loss will be infinity. So you can see that in misclassification, this loss term, this binary cross entropy loss will be it will be going to infinity. Okay, in this case when it is right, so this will be going to 0. Loss will be 0 in this case and loss will be infinity in this case. That you can clearly see from here. And I also justified why do you use y and 1 minus y over here, because these are probabilities and we have only two values. If one takes value, let's suppose some value a, other will take 1 minus a, because the sum of probability should be equal to 1. Any questions on this binary cross entropy loss? Okay, now the second case will be categorical cross entropy. Because we have categorical classification where you have categories now, multi-class classification. The first class was binary classification where you had two classes only. Now you will have multi-class classification. So there you will have some categories. So as I said that you have data point D that is equal to xi, yi. So these are the features and this is our label. So yi here belongs to one the categories. So categories can be 0 to k. So this is a multi-class classification problem, or we can call it categorical classification, where you assign one category to the problem. So for this we define what is called as categorical cross entropy. Categorical cross-entropy loss. Okay, so for this, what you can do is, so you again use the same formulation that we used earlier. So you have this cross entropy h of p comma q, and you will have the formulation that we used earlier. So I is equal to 1 to c, you will have c categories, let's suppose. So probability pi, and then you will have log of qi, something of this sort. So now you can convert it into like this. So you have one hot encode. Let's suppose if you use one hot encoding, so you use something of this sort. Suppose we have 4 classes, 1 0 0 0. Okay, so this is true distribution, and you will also have some prediction. So the prediction will be a distribution of this sort. So this is 0.2, 0.4, 0.1 and 0.1 for the 4 classes. This is our prediction, and this is our true distribution. This is suppose p, and this is our q. Now if you see, all these things will go to 0. So if you expand this, so 0 multiplied by, let's say this is true, pi will be 0. Pi will be 0 for these 3 cases, and you'll be only left with the class that we have. So if you just take this cross entropy, you will get this to be equal to log of qi. Okay, because for all other things you will get 0. Let's suppose in this case you are left with only 1 point. So this is what you will be left with. So generally you will see only one thing written. So because for pi it is either 1 or 0. For 1 it will be left with qi. Let's say in this case it will be q1, and for all the other q's this pi will be 0, and it will multiply this 0 with log of qi, and they'll be turning to 0. If I expand this, rather I should expand it. This will be pi p1 log of q1 plus p2 log of q2 plus p2 log of p3 log of q3 plus p4 log q4. Now if you see this, so in this case p1 is 1, rest is 0. So this over here will be cancelled, this cancel, this cancel. So they'll go to 0 because p2, p3 and p4 are equal to 0. Only will be left with p1 to log 1, but p1 is 1, so we'll be given p1 1 multiplied by this. So this is equal to log of qi. So in this case log of q1. So for a particular class, so if you are asked what is the categorical cross entropy loss, you can just say log of qi. I is the class which the data point belongs to, the ground truth basically. So for that point we'll just optimize for that point. Yes, please, questions? Yes, good point. So it will be negative all around. Okay, so here this is also negative sign, so I was missing that negative sign. So this will be minus log of qi, not just log of qi, this will be minus. Okay, we can do some example also. So in that case you can clearly mention, let's suppose a probability distribution. I'll just give you this, so once you watch the recording, so you'll do it by yourself. You have 0 1 0, so this is the ground reality. When you sample data point, these are true class labels, and then you have this q, the prediction. Suppose the prediction is this, because you know that once we apply softmax we'll get a distribution. So we'll get distribution in the output neurons, so you'll get something of this sort. Now you'll have to compute h p comma q. Now you know you have to only compute for this, so this will be actually the answer will be log 0.7. I think this will be the answer. So this will go to 0 and this will go to 0. We'll be left with a log of 0.7. I think log of 0.7 is roughly equal to 0.357. Okay, these many number of nats or whatever. If it's log 2, so it will be based on that. Okay, and these are the two cross entropies which you will frequently see. You will see binary cross entropy loss or categorical cross entropy. Okay, let me give you some real world examples to see why we will use this. Binary cross entropy is pretty clear. So why will you use this? So if you have emails like spam or ham emails or any classification problem, suppose you have to predict if something is dog or a cat, dog or not dog, or dog or cat, something of this sort, or something else. So in this categorical cross entropy loss, so it usually is used in language models. So you'll use this cross entropy loss there. Why? Because there you have a vocabulary. So you have a context, given a context. Yesterday we took the example. So you are given a context. Let's suppose we are in a dash, because right now we are in the class. So this is our context. So this thing is our context. Given this context, so you will actually apply the probability, because as I said, the last layer of that neural network, the output layer, will contain how many neurons? The number of neurons in the last layer, the number of neurons or computation units rather in the last layer or in the output layer. In the output layer, the number of neurons in the output layer is equal to cardinality of vocabulary. Cardinality or vocabulary size. I can just say vocab size. Okay, you know that what is vocabulary? Vocabulary is the total number of tokens that language model can predict. Okay, that is equal to that. And then what you would basically do is, in that you will apply softmax on this. So you will apply softmax on these neurons. So once you apply softmax on this, and if this problem, as I previously also said, this is called as self-supervised learning. So here this is a supervised training. So here you know that what is the word. So let's suppose the word is class, and it will give the probability distribution to all the words in the vocabulary. Whatever vocabulary you have, 0.1, let's say 0.001, 0.002, because there will be maybe roughly around thousands of words or thousands of tokens. So it will give the probability distribution to everything, and then you will have to do the cross-entropy loss. So what you will do is, you will use this categorical cross-entropy. You will say that actual probability of this word should have been 1. So the class should have been 1, because you will have one hot encoder vector. The class has the probability 1, but it has given probability distribution to everything. So you will try to optimize, you will try to compute this. What was the probability that was given to class? If the class was given probability as a 0.2, so you will say log of 0.2 negative of this. So this is the cross-entropy loss for that particular example, and you want to reduce that. And next time when you are training on this, so you will again give it, you will try to give the higher probability to the predicted one, to the actual token which has to be predicted given the context. Okay, this is one example where you use categorical cross-entropy loss. Okay, in language model. So I'll write it here. In language model, this is where you use it. I hope you got this right. Any questions till here? Now you at least understood binary cross-entropy loss, and you understood categorical cross-entropy loss, and you saw different applications where they usually are used in the real world. Let's now move on again, because we were discussing about KL divergences. You probably might be interested in it in some different way. So we'll have a generic concept which is called as F divergence, because we were trying to find that divergence function. If you have probability distribution P, let's suppose P of theta, and then you have other probability distribution P of X. Okay, and this may be your predicted one, this can be your ground truth. So this is your ground truth, this can be predicted one. So how can you tell me a discrepancy? We said, say this is f of x w, and this is my prediction y, and then we said that we had divergence function of this sort, which takes input as these two things, and it can give me some value. It can give me some sense of how much off they are, how much different they are. Okay, now we'll introduce the concept of what's called as F divergences. So what is this F divergence? So this F divergence, basically it's a unifying framework. You might have just heard about KL divergences, but there are more than KL divergences. So F divergence, this represents a broad category of this divergence. It's a unifying theory. It's a unifying framework in information theory. So I can say unifying framework in information theory. IT. By IT, I mean information theory. So it will give a generic template. It will give a generic template of these divergences. All of these divergences are all called F divergences. And then in that, you just have to change this F function. Okay. Let's see what this F divergence says. So you are having this divergence function. Consider this as d of f. So df, and you have two distributions, P and Q. So you write this as like this, P and Q. What is the F divergence between P and Q? So P is one distribution and Q is another distribution. You may not know both of these distributions. You may know one of them. You may know both of them, and you just want to compute. So how one distribution is different from other distribution, how much is the discrepancy, or how much similar are they? Okay, and they are both are defined on state space X. Consider that. Okay, so you have this F divergence. So how do you now define that? By definition, this is equal to Q of X, and then F of P of X divided by Q of X dx. So this is if you have this P and Q, these distributions are continuous. So if P and Q are continuous distributions, because you know that distributions can be discrete distributions or it can be continuous distribution, and we have read in probability that if P and Q are discrete distributions, so we'll change this into summation. Okay, this thing will be changed into summation, and rest will follow like that. Okay, and this is called as F divergence, as I wrote in the heading. This is by definition. And this term over here, if you see P of X divided by Q of X, this is called as likelihood. So why this term is there? If you have two distributions, P of X, P, and you have other distribution Q, you want to see how similar they are. Okay, so how you can compute them? You are computing some sort of ratio. You are saying that I can divide P by Q. If they are exactly equal, I'll get ratio around 1. Okay, if there is some discrepancy, it will be off, it will be less than greater than 1, howsoever, because difference will not be equal to 1. So somehow you are computing this likelihood over here. And now you are given this chance. this function. So you have a chance of choosing this function, and this function should have certain properties. It should be what's called as absolute continuous with respect to q, okay, and there are other values as well. I won't go into the properties of this. And this f should be convex function. What is convex function? I would define it here. I think many of you might know this. So this function has certain properties that it should follow, and one of the functions that we have in our case, so we can use t log t. So if we have this function f of t, so if this function f of t is equal to t log t, so this over here is KL divergence. So we'll get KL divergence. So if this f of t, so here you have this f of p of x q of x. So in this case, if I say f of x also, f of x is x log x. So if you use this function, okay, so you will be getting this KL divergence. So now let's go to KL divergence, and I can give you different functions. So if you have, suppose this, if you have now KL divergence of p and q distribution, if you are given two distribution, it can be for discrete case, it can be for continuous case, because these p and q, they can be discrete random variable or continuous random variable. Let's do it for the discrete case. KL divergence is p of given q. Now this integral will change to summation. So what I can write is, I can say summation of I basically is the sample space that it has, p of xi, and then this log of p xi divided by q of xi. Okay, this is the function I have used over here. So if you see this over here, so this somehow looks like entropy, the earlier one that we discussed, and now you can use the properties of log to expand this. So how can you expand this? So you can expand it like this. This is summation of I. Keep an eye if I do some algebraic mistake. So this is probability of xi log of probability of xi. Okay, I am just multiplying this with this. So this is division. So this will be now subtraction. This will be log of minus qi. But this px is multiplication of both, and the summation is what this. And then minus. This is q p of xi log of qi. If I give summation separately to both of these, so I can say summation of I p of xi log of p of xi minus p of xi log of q of xi. So if you see this over here, this term, this should be also given summation I. If you see this term over here, this is entropy. And if you see this term over here, this is cross entropy. Can you see this? Everybody clear on this? So what I said is, so in our case, so what we can do is we can say if f of x is x log x, so we can just replace this. So this was the given formulation, and in this case we are considering that this is a continuous random variable. If we take the discrete case, we'll have to do summation of this x. So now after applying log of this, so this is x log of x. So what we can do is, so once we expand this, so you will get entropy minus cross entropy. That's what I called KL divergence when I was introducing entropy and cross entropy. Difference between cross entropy and entropy is KL divergence. Any questions on this? So I can write this as h of p minus h of p comma q, something of this sort. I think it should be the other way around. So are we missing somewhere something? That's why I told you, give me have a look at my algebraic manipulations. Okay, there was a slight mistake over here. So this should be q of xi, because divergence, f divergence, if you see how it was defined, so this was defined like this. So it was defined like q of xi, then function of p of xi divided by q of xi, and this over here was called as likelihood. So this term was likelihood. So when I said that when I said f of x, this function is equal to x log x. So if I insert this function, so as I said, there should be properties of these functions should have different properties. So now if you insert these values over here, and it will have integral with it or summation with it, depends on if you are doing it with continuous case or discrete case. So let's suppose we are doing it with discrete case. Now summation of q of xi, and then this this will be multiplied by p of xi divided by q of xi, and then log of this whole term p of xi divided by q of xi. Now you can see this and this will be cancelled, so you'll be left with summation of p of xi log of p of xi divided by q of xi. So that's what is written over there. So here if you see q of xi log of p of xi. Now if you did the logarithm manipulation, so you will be left with this. Now if you see this term over here, so this is not cross entropy, so this is negative of cross entropy, and then minus, and this term over here, so this is minus of cross entropy. So this is our entropy, only entropy. This is negative of entropy, and this is negative of cross entropy. Now if you see, now the thing that we will get is, we will get KL divergence is equal to h of p comma q, that is the cross entropy, minus the entropy. The entropy is h of p. So this is what KL divergence is. Everybody clear so far? So we saw two things. So we saw it from the entropy perspective. We first defined what entropy is, and then we said, okay, what is the difference between, we also defined cross entropy. Then so if we take a difference, if we actually want to quantify this difference, so that is given by the KL divergence. Now we also saw that by F divergence. What I said? So I said F divergence is a unifying framework in information theory. What does it unify? It unifies a lot of divergences. So you have this function F over here. You have liberty to take this function as it is, but the function should have some properties. The function should be convex. It should be non-negativity. It should have what's called as identifiability. It should have convexity, and it should have symmetry. So this function should be there. But taking those things aside, I'm telling you that one function is log. Log is the one function. So if you take f of x is equal to x log of x, so this will be equal to KL divergence. Okay, I'll just now name few of other divergences. So this is called as KL divergence forward method. So because KL divergence is asymmetric, by that I mean, so if you calculate KL divergence p and q, so this will be different from KL divergence of q and p. So this is not equal. So it's asymmetric divergence. So if you now take f of x is equal to, let's suppose, minus log of x, if you take this, so this is called as reverse KL divergence. Reverse KL divergence. So now I'm just seeing the functions. I told you what F divergence is. F divergence is a unifying framework. So what you can do is you can just change f, and it will tell you how much difference is there in the distributions between distributions p and q. If you now have this function x log x, and this will be KL divergence forward, and if you have f of x is minus log of x, you will have KL divergence but in reverse. Why is it defined separately, reverse and forward? As I said that this KL divergence is not symmetric at all. It's not symmetric, so this is not equal to this. So if you have KL divergence between p and q, this is not equal to KL divergence between q and p. So now if you have, let's suppose this f of x is equal to x minus 1 whole square, so this is called as Pearson's chi-square divergence. Okay, then you have Square-Hillinger, Jensen-Shannon. So there are a lot of other functions which I can write over here. So this all comes under these divergences, but one of the interesting cases for us was this KL divergence. Any questions till here? Any questions? So if you now saw, I'll just summarize the things that we did so far. Okay, be attentive here. So we first defined what an entropy is, and then we said what cross entropy is, and then we defined KL divergence. Okay, and then we said this was from the entropy perspective. Then we defined F divergence over here, and then from F divergence we again derived this KL divergence. It again had some link with KL divergence and entropy. So KL divergence had link with entropy again. So now we'll see a probabilistic perspective on this loss. So I'll give a heading probabilistic. Perspective on these loss functions. Okay, and I'll now tell you the scheme or the method or an algorithm to consider a loss function. Now you have enough background in information theory because you know what entropy is, you know what cross entropy is, KL divergence are. So now how can you construct loss functions? Okay, now we'll see the probabilistic from the probabilistic lens, and you will see that. Now you know that we have a function f and x, and this is a parameterized function. This is what a neural network is. So you are sort of giving an input x to that, and you have some weights that you have that you can change. You have these parameters w, and I can write theta or phi to these, but we have stick with the notation w. So this w basically a set of parameters. You can adjust these parameters to get a prediction of that. So basically what it is saying is, it is saying that if we are having these pairs x comma y, so our data looks like this. So data looks like xi, yi. So you have these pairs. Now what is this basically telling? This is telling you compute the probability of y given that you have this data point and you have these parameters for the model. You are given this input and you are given these weights for the model. So what is the probability? So this is what basically you are computing when you are giving this. So in turn I can write you are computing probability given y and given this model. Okay, this is what you want to basically maximize. Now you want to do it for every point. Say, so this thing over here. So if I say probability of y, probability that label, given that you have this data point xi, you have a particular data point. So I can write probability of yi. What is the probability of yi given you are given this point xi and you are given certain parameters at a certain position, let's suppose consider them as w, or maybe you can also consider wi, because we'll have family of these models, depends on how w changes. Okay, so now this is what you have to basically maximize. So if this is this thing over here that you see, so you have to maximize this for all the points. So this is for all the points, I goes from 1 to, let's suppose we have n data points over here, and you will have to find such a w. You will have to find such optimal w for which this is maximized. So how can we write that? We'll say that optimal w or w star is equal to multiply all these two things together, and then probability yi, given you have xi and you have this w, and this over here is called as maximum likelihood criteria. Maximum likelihood criterion. Okay, if I again like say what we're doing. So we had this function, we had this neural network which was given some input and it had some weights. So now if you have to turn this into probabilistic length, if you have to see it from the probabilistic length, so I'm saying basically what are we doing? We're saying what is the probability of y given this data point and these weights. So we'll compute it for everything. So we'll compute it basically if we have two classes, say we have y1 and y2 suppose. So I'll compute probability of y1 given this point x and these weights, probability of y2 given this point x and w. Okay, I'll assign probability to both of these things if you see over here. So now I want to assign higher probability to the right class. Suppose this point x belongs to class 1, suppose. So if this belongs to class 1, if this belongs to this y1 class, so I'll assign higher probability to this. Okay, I'll assign lower probability to this. Ideally, I should assign probability 1 to this and probability 0 to this. Okay, that's what I have written over here. So what I'm trying to do is I am trying to get the maximum probability and I am multiplying these probabilities together. Okay, so I am doing argmax of this. So I should do argmax over w. I should adjust these w's in such a way so that this wi given that xi, for this I should get the maximum value for these things over here. So this thing, as I said, is called as maximum likelihood criteria. Okay, so that is what you want to maximize. So this is the optimization problem you have. But the assumption that we're taking two assumptions over here. So the first assumption is, so we're taking two assumptions that we are trying to take here. The first assumption is that when you are taking these data points, they are identically distributed. So data points are identically distributed. What is the meaning of that? So the meaning of that is distribution is not suddenly changing. So when you are having one point, so when you take the other point, it's again also coming from that same distribution. So as I usually give the example, when that Nokia phones were trained, they were trained on European people. Now they were tested on suppose African people. Now distribution is not same. So that's not identically distributed. So if you are training model on one distribution, you should also test model on the same distribution. So that's the first assumption here, that your data points are identically distributed. That is, so all the data points come from the same distribution. That can be written in this, if probability of y given x. So this, if this is the distribution, so this should hold for all the points. And second thing is that these data points are sampled independently. Okay, so they are independent examples. So the outputs are conditioned, they are conditionally independent given their inputs. If you are given an input and if you are given an output, they do not have any dependence on each other. So how can I write it mathematically? So if you are given probability of yi given xi, okay, and then I am saying that let's suppose consider the say this probability of y1 comma y2 till yn given the points x1 x2 till xn, suppose something of this sort. If I am given this, so I should write it by independence of probability. I should write this as multiplication. I goes from 1 to say n, probability of yi given xi. So this is the meaning of independence. If you have seen our probability lectures, you probably will understand that. I think you all have attended probability lectures. So these are the two assumptions that we take. So this is what we call as IID. So what is IID then? So IID basically means this is independent and identically distributed. So independent and identically distributed. Okay, again telling you the same problem. We had a model and then we said that this basically can be seen from a probability, that probability for a class given you have a data point and the weights. So this can be also written like this. Now what we have to do is we have to maximize the probability for the right classes. So we are saying that, so we'll find such a w for which the probability xi and y, this should be maximum. So basically probability of y1 given point x1, so this should be maximum. For other point x2, so y2 should be maximum. So for the probability of the right class should be maximum, as in this case, if x was from y1, okay, and we had two classes y1 and y2, and we wanted this to be maximum. And if we multiply all these probabilities together, so you will get basically this, you will get probability yi given xi and w. If you take all the points, because we're assuming that these data points are identically distributed, and the first thing is they are identically distributed and they are independent. So we can use the independence. We can say that if you multiply these two things together, you want to maximize this. You want to find such a w which will maximize this number. Okay, for a particular xi, so that yi, corresponding yi should be given the most probability. All other, if let's suppose this is yj, that should be given less probability. If I say probability of yj, some other j given xi, so this should be given less probability. That's what I told over here. Everybody satisfied with this? And this thing over here is called as maximum likelihood criterion. Any questions on this? Okay, now if you see that two assumptions, we have these data points IID. Now we have this what's called as maximum likelihood criterion. So now if you see again the problem here, so we are having these probabilities will be less than 1 and they will be greater than 0. So these things over here, if you see this, or that I wrote over here, the argmax. If you see these probabilities, because you know probability are between 0 and 1, so you know this, and all these probability will be less than 1, and there are a number which is less than 1. So you have w star, the ideal w star should be, you should argmax of w, the w should be adjusted such that probability of yi given a particular point xi and w for all the data points, you should multiply this, okay, for all the data points 1 to n. Now the problem is that this quantity over here, this will be less than 1, or at max this will be 1. So if you keep on multiplying quantity which are less than 1, let's suppose 0.8 multiplied by 0.3 multiplied by 0.4, something of this will again tend to 0. So this quantity keep on multiply, so this will be diminishing. And again the problem you will have in computers, because you have limited, you have finite memory, so because of that this will approach to 0, or this will even sometimes do underflow. That is the problem. So we won't use this as it is. So we won't use this maximum likelihood criterion. So what we'll use is we'll apply log on that. So if we apply log onto this, so this multiplication will be converted into addition. So if you apply log on this, so you have maximum likelihood criterion. So now what you do is you apply log onto this. So this is called as log likelihood. You might have heard about log likelihood, maximum log likelihood. So because now you are applying log onto this. So what will happen is, because log is a monotonic function. What is the meaning of monotonicity? So if let's suppose you are having a function, you have this function. If it is, let's suppose, increasing over here. So if you see log function, that is something of this sort. So it is always its monotonic function. So if you apply log onto something, if something is an increasing function and you apply log onto that, it will still remain that function. Okay. So because, and you are interested in finding the max value, you are trying to find that value for which it will maximum. So maximum won't be changing, so it won't change the function. That is the meaning of monotonicity. So log is monotonic function. So by that I mean that if you apply this monotonic function onto some other function, it won't change its maximum or minimum values. It won't change its max values. So where the max value was initially, if it was, let's suppose, at x is equal to 5, it will still remain at x is equal to 5 if you apply log onto that. That's why we can apply log, and we are interested here in finding the maximum value. So here the problem that we had, maximum likelihood criterion, that got converted into log likelihood. So we'll have this w star is equal to argmax. Did I write min somewhere? Argmax everywhere? I suppose argmax is everywhere. Yes. So argmax basically means give me that value for which the value is maximum. Argmax on w, give me such a w so that this value gets maximum. Now I am applying log onto this. Log of this product goes from 1 to n, that's for all the samples. Probability of yi given this xi and this parameter is w. So this thing over here is called as log likelihood. Now in machine learning, the problem is that we do not want to maximize, we want to minimize things, because loss usually we want to minimize. You don't want to find likelihood, you want to find loss. Okay, if let's suppose if something function is f of x, okay, and if you want to find, let's suppose, some max value of it, if you convert this function into f of x, whatever the max was, it will be converted into minimum value, because you're inverting the function, you're giving it negative value. So now you had maximum likelihood function. The problem there was it had a lot of multiplications and all the values were less than 1. So now if you multiply all these things together, what will happen? Underflow might happen, because we have finite memory. So we said, okay, we can solve this. We can convert these multiplications into addition. How can you do that? You can apply log onto this and you can convert these multiply into addition. Good. Now the problem is, usually in machine learning we want loss to be minimized. So here we are talking about likelihood. So what we should do is, then we should not talk about likelihood in this term, we should negate the likelihood. Then we'll call it negative log likelihood. All of these terms you might have heard. Negative log likelihood. And this thing over here, if I apply negation sign on this, if I now convert this optimal W star, so I want to find such a function for which this, I want to find argmin of this. So minus argmin of W, minus of log. So argmin of minus log of pi is equal to 1 to n probability of yi given xi and w. This over here is called as negative log likelihood. The function that I wrote over here, this is called as negative log likelihood. This is the loss that we sometimes will again see. Okay, and I can now show you that this is equal to binary cross-entropy loss in case of binary classification. This is equal to categorical cross-entropy loss in terms of categorical or multi-class classification problem. So if you see this, this is taking that shape. Okay, this will be getting converted to summation. Okay, can you see that over here? Is everything clear so far? So we started with maximum likelihood criterion. So we started with maximum likelihood, and then we converted that into log likelihood. Okay, this was converted into negative log likelihood, something of this sort. And then this is what we want to minimize. We'll minimize this, because in machine learning we consider loss. So loss should be minimized. We should not maximize a thing. Okay, here we had maximum likelihood should be maximized, but loss should be minimized. So we are saying negative log likelihood, though this is somewhat like loss. That's why it's named as loss. Can I assume that you people understood everything? So as I was telling you people that why are we covering this loss function in such a detail? Because we will be back propagating through these loss functions. Because we want to minimize loss. So how to minimize loss? So because we'll be using this loss function and we'll be using calculus or in particular differentiation, so that we can get the optimal values. In this particular case, we will get we'll take the first derivative so as to minimize the loss, so as to reduce the loss in iterative way, and we'll apply gradient descent on these things. So if you know what is this loss function, if you know cross-entropy, binary cross-entropy, KL divergences, log likelihood, they have different names. So you will have a different appreciation when you will do the back propagation algorithm, when you will adjust these weights and bias, and you will see that the loss is actually adjusting, the loss is decreasing, it is increasing if I do some adjustment in the parameters. Then because you know the loss, you know how it behaves, you know the behavior of these loss functions, you will have a way different appreciation than the people who are just doing it mechanically. They are given this is a loss function, apply derivatives on this, they still have some understanding, but the people who know what loss functions are and how is this constructed, why is it important, why should I not use this loss function, and why should I use this loss function in this case, they have a different appreciation when they do this back propagation algorithm. Now how to inference now? So now because you have found this, so you have this you had arg minimum of this, so you are doing minimization of log likelihood, negative log likelihood, that's sometimes written as minus LL. So this is negative log likelihood. So once you have this negative log likelihood, how do you do the inference? Because your model is now predicting the distribution, because I said at the end of the layer, you usually, if this is a classification problem or a multi-class class, you are giving output as a distribution. So now you are giving output distribution something of this sort, 0.2, 0.5, 0.1, 0.4, something of this sort. So now what is this y hat equal to? How to now, if you have to give what's called as point estimate, if you have to just assign one label, okay, because it's a classification problem, you have to give just one class. So what you do is you take argmax of this. Argmax, what is the argmax? Argmax basically means the maximum value of y. So if you have probability of y given this x and these parameters and these optimal parameters, say w star. So this is our inference. This is our prediction. Prediction or inference. So when you infer these model, so you basically see at what label is the probability highest. So that's why I'm saying that y hat, that is prediction, is equal to argmax of y on this probability. So as I said, you will have classes, let's suppose y1, y2, y3 and y4, say you have these 4 classes. And now this will give probability 0.1, 0.4, 0.1, and then you will have suppose this is 0.2 and this is 0.3. So now if you take argmax of this, so argmax is an operator. So when you apply this, so this basically will give you such a y on which the value is maximum. So for this y2 value is maximum. So y hat in this case is equal to y2. So this is the inference step. So but how do you get it from? You get it from likelihood, and you want to like decrease the loss, basically you want to minimize this negative log likelihood. Likelihood is you want to increase that, but negative likelihood is the opposite of likelihood. That's why you want to minimize this. You might have seen me writing this argmax and argmin. Argmin basically is an operator which gives you that value for which the whole expression gets the minimum value, and argmax is again operator for which argmax of y basically means such a y for which this whole expression gets the maximum value, and argmin, if I write argmin of y, that means such a y for which this expression gets the minimum value. So that's the difference. So we now saw that you started from likelihood and then you went to log likelihood because of underflow operation. Then you went to log likelihood because you have to give it some sense of loss. It should not be, you have to increase something. Always in deep learning, machine learning, you'll be talking about loss. Okay, and loss you have to decrease. You don't have to increase that. That's why we went to this log likelihood. And I also told you how to do inference. So what you do is you take the argmax of that y, such a y for which the whole expression gets the maximum value. Okay, so this is how you do the inference. This is called as point estimate also. Point estimate. Because you just want to give one class. If you have to give multiple classes, you will maybe do some other things over there. And now you have to find an algorithm or a recipe to construct a loss function. How to construct the loss function now? Given this background, how to construct a loss function? So this is the question. If you are given a problem, now for that, if you have to construct a loss function, what to do? The first thing is, because we have spoken about probability distributions a lot, we have learnt about discrete probability distributions like Bernoulli distributions, we have learnt about let's suppose binomial distributions, Poisson distribution, a lot of distributions that we have covered, and in the continuous case we'll also cover Gaussian distributions, a lot of other distributions as well. The first step in here, when you have to construct a loss function, so you have to choose a probability distribution. Okay, for step 1, select a suitable probability distribution. Select a suitable probability distribution. Okay, this is the first case. So now what to select for which? Usually for real valued or regression problems. So for real valued outputs, so you use Gaussian distribution. Okay, Gaussian distribution. And then if you have binary classification, you will use Bernoulli distribution. And if you have multi-class classification, you will use categorical distribution. If you have counts, you use Poisson distribution. If you have angles and directions, you use circular distribution. Okay, it depends on the problem at your hand. Okay, the first thing is you have to select a distribution. So why do we select distribution? Because you believe that this choice encodes an assumption that data determines some form of this. So some form. And then second thing is you have to parameterize that distribution using the model. So first thing is you select the distribution because you are now modeling this process, and you know that each distribution has some parameters. If you remember the lectures from probability, you know that each distribution has some parameter. Let's suppose Bernoulli distribution, it has parameter p. Binomial distribution has two parameters, n and p. Gaussian distribution has parameters sigma and mu, that is variance and mean. So I'll just write them. So if you talk about Bernoulli distribution had a parameter known as p, probability. Binomial distribution had two parameters, n comma p. So it had number of trials and the probability in each trial, and we said that this binomial distribution is a repeated Bernoulli distribution. And Bernoulli distribution it is some way you have two possibilities, it has the tails. So we applied Bernoulli distribution, success and failure. So success probability is p. Everybody so far? Everybody here with me? Okay, now as I said that these distributions have some parameters. Now you have to find these parameters by that model. That's what the second step is. You have to parameterize the distribution using model. You have to parameterize the distribution. Okay, let me just write these somewhere else. Take it here. Parameterize the distributions using your model, because you are using a parameterized model, a neural network. So how to do that? Because you have some parameters theta. So let's suppose you have, and theta can be p in this case and np in binomial case. In Gaussian distribution you have sigma and mu. Sigma square is variance and mu is mean there. Now theta in this case will be sum of these. So you have to parameterize this. So you are having this f of x and weights. You have these weights and biases. You have the model parameters and you are having x, and you are estimating these parameters, the distribution parameters, by using the model. Okay, this basically is equivalent to probability of, now after you estimate this, after you adjust w to get these parameters. So you are trying to probability of y given this theta, given the parameters of this model. This basically will be equivalent to probability of y of f of x comma w or xw. This is what you want to find. This is the second step. This again maximum likelihood estimate, some sort of things like that. So you want to estimate the parameters of the distribution, either p, np or p, because you want to fit that distribution somehow, and you will find those parameters by using the model. Okay, and your model is parameterized by these w, the model parameters. So these are model parameters. You might confuse between these parameters. I will explicitly write, and these are distribution parameters. These are distribution parameters, these are model parameters. And now you know that this thing, and you have to basically find this probability for a y given that theta, and you have to come up with these. This is the second step. Third step is define this negative log likelihood. So step 3 or third step over here is define the loss as negative log likelihood. Define loss as negative log likelihood, NNL. Okay, so now you have to compute the training objective. So what should you do? So you should say that, let's suppose I have this L of W. So L of W is a loss function. So you want to find such a W, optimal W, and you want to see arg min of W on this L of W. This is your optimization problem, because now you want to do it with log likelihood. So how to do that? L of W is equal to minus summation of I is equal to 1 to, let's suppose, I or whatever, and then you want to see log of probability yi for particular x comma w. Okay, now I am converting that pi into this, because after applying log I can convert all these multiplications by this addition. So this over here is applying that log likelihood on the distribution. Okay, we write this box in a better way. Okay, so this is that. So this is your negative log likelihood loss. So this is your loss, which is negative log likelihood. And fourth thing is, now you have to perform inference. Step 4 or fourth, perform the inference. Perform inference basically means do the forward pass. Perform inference. Inference basically means you have to do point, that's called as maximum point estimate, MAP prediction. So return a point estimate. So how to do that? So y prediction is equal to argmax. So you want to get the maximum value for a y such that this probability for a particular, whatever the class is, that you should get maximum value for that. Okay, I hope that you are clear with this now. And now let's take an example. We'll take example of binary classification. I'll tell you that we'll land up at binary cross-entropy loss by using the algorithm that I just laid out. So example is for binary classification. So before doing this, let's again see the 4 steps. The first step is choose a distribution, and second step is, so once you choose the distribution, so as I said, for real valued output you can take Gaussian distribution. For classification you can take Bernoulli distribution, and for other distribution you accordingly take some distributions at hand. And second thing is you parameterize the distribution using your model, something of this sort. You will estimate the parameters by using the model. Okay, that's how you, and then on that you will define the loss function. You will define this loss function, and after that you will do the inference. Now let's suppose we have binary classification where we have 2 classes. Okay, so y belongs to 0 or 1. Label can be positive, negative, success, failure, something of this sort. So now binary classification, this is, as you know, most common task in machine learning. Now we have to choose probability distribution for this. As I said, we will use Bernoulli. This is the step 1. Choose the distribution. I am choosing Bernoulli distribution. Bernoulli distribution. And you know what Bernoulli distribution is? So Bernoulli distribution has, let's suppose it's parameterized with W. So we have lambda gives 0 or 1. So this is what it has. Let's suppose if I define this, if I define probability of y given lambda. So if you are given some lambda, we'll say that this is 1 minus lambda, or p, the probability, because I don't want to confuse this p with some other thing. So here I am using lambda, the standard notation. Probability y given lambda. So this lambda is the parameter. And this is equal to when y is equal to 0. And when y is equal to 1, so this is the probability. So this is how we define the probability mass function of that. Okay, or compactly we can write it like this. Probability of y given lambda. So this is equal to 1 minus lambda multiplied by 1 minus y, and multiplied by lambda multiplied by y. I think this also you have seen previously in the probability classes. This is what how I write it. So now I have selected distribution. The problem was of binary classification, and binary classification problem once selected, I said that now I have to choose a distribution. I chose the distribution Bernoulli distribution. I know that This lambda is the probability of success, because you can have success or failure, and the parameter over here is probability of success. So probability of y given this lambda, so it is defined like this. So I can write probability mass function like this. Any doubts till here? So now we selected this. If you again see the steps, the first step was to select at suitable distribution. So because we had binary classification, we selected Bernoulli distribution. And the second thing is you have to parameterize the distribution using your model. Okay, now if you see the model, let's suppose we have this model. Now model gives the outputs. So if you see f of x comma w, so this will be our outputs or logits, which we call. So we'll have these logits. So they can be from minus infinity to infinity. We'll have to apply some function onto them so as to give them some probabilistic meaning. Let's suppose if it's a binary class, we'll have just single neuron, say. At the end, we'll have single neuron. So we can apply logistic sigmoid function on this. Logistic sigmoid function. So what is that function? We have covered that in detail. I suppose you people will be understanding that. So sigma of, let's suppose z, if the z is this like output function, the logit, and you apply sigma of z, that is 1 divided by 1 plus e minus of z. This is the function that we usually apply, so that it converts into probability distribution. So this will, the value will be between 0 to 1. This is what the logistic function does. Okay, once we have this, now what we can do is we can say that this lambda, because we have to parameterize, distribution parameter should be parameterized by the model parameter. So what to do that? So we can say this lambda is equal to sigma of f of x comma w. Okay, so this is how I can write this. Now step 3 is, this was step 2. This was step 2. Step 1 was to choose a distribution. Step 2, I parameterize that with the model, because I know that at the output of the model I'm using this sigmoid so as to convert that into probability. Step 3 is, now you have to write it into log likelihood. So what is log likelihood? You already know that. So now if I write probability of yi given xi and the model parameters, because I have to write it for a single training example. I'll just write for one training example, xi, which has corresponding yi label. So what is this equal to? So this will be equal to 1 minus sigmoid of f of xi comma w, because I am applying sigmoid, and multiply, this is basically lambda, 1 minus lambda. If you see, that's here, 1 minus lambda 1 by y, to the probability I am applying this probability. So 1 minus lambda 1 minus y and lambda of y, so this is multiplied. So I am saying 1 minus sigma of f of x of y, and then at this I am writing 1 minus yi, and then multiplied by sigmoid of f of xi w yi. So if you see this over here, so this is somehow like this. Now you know that if I apply this log likelihood on this, if I now convert this, the step 4 is apply log likelihood. Step 4, convert this into log likelihood. Once I apply log onto this, so this thing, if I apply log onto this, so this will be L of, let's suppose w, so this will be converted to x is equal to I is equal to 1 to I and minus of, so I'll apply log onto this. So this function will be applied, I'll apply log on this, so you'll get 1 minus yi. So I'm just copying the equation, but I hope you will do the calculation. Basically when I'm applying log on this, so I am applying log on this, so once I apply log on this function, this 1 minus I will go down, so this will come down over here, and you will be left with, and again you will apply this log on this yi will go down, so you will be left with summation of this, and then 1 minus yi log of, let me just see, 1 minus sigma of f of xi and w, and plus, this is with the whole braces, plus second thing is yi, because now I also apply log on this. This is negative log, I am applying negative log likelihood, so yi, and again log of this sigma will remain as it is, sigma of f of xi w, and this will be closed. So if you see this over here, this is again binary cross entropy loss. So this loss over here is binary cross entropy loss. So how many of you can recognize this binary cross entropy loss? So let's suppose this is predicted yi, this is our prediction, so I can write it L of w is equal to minus sigma of I is equal to 1 to I, and then 1 minus yi, this is the ground truth, and then log of 1 minus, this is prediction by the network, so y minus y hat, and then plus, this is yi, this is prediction of this is log of prediction of network. Can you see that this again is binary cross entropy? How many of you appreciate this now? We did the same 4 steps. I again came up to binary cross entropy loss by using the maximum likelihood criterion. Okay, now you saw an algorithm. You saw a loss function algorithm by the help of which you can construct loss. Again, going with that, the first thing you are doing is you are selecting a suitable probability distribution. Okay, whatever the problem is, there will be some probability distribution which matches it. So in our case, let's suppose where we took a classification problem, because in classification you will have class 0 or class 1. Consider this as class success, consider this to be class success, and this to be class failure. Okay, and then there will be some probability of success. So when you sample these images, or let's suppose these emails, there will be some probability of success. Consider that probability is lambda, that is the parameter we had. So if you see this is the exact template that was there for Bernoulli distribution. So what was Bernoulli distribution? So Bernoulli distribution of lambda was, if you have some experiments where there is this template that you have success and failure. So when I was teaching you this, I said in the real world there are a lot of problems which are like this, where you have success failure. So we took example their head tail to just make the point through. Otherwise you could have taken any example. So in this binary classification case, this exactly is like Bernoulli trials. So if you perform Bernoulli trials, so basically you are just taking an image. If it is scattered dog, you are saying there is a Bernoulli trial. You are taking, let's suppose, an email, it is a Bernoulli trial. It can be ham, it can be normal email, no spam, or it can be spam emails, or it can be ham emails. So some of one of them, it can be failure or a success. So you are now adjusting this. You are saying that, okay, so this thing is like that distribution. Now if I model this with my probability distribution, so I am saying that basically I have to find this lambda. That's what I said in the second step. The step first was choose a probability distribution, and that should be chosen on the basis of problem. So as I said, if you have binary classification, you will choose Bernoulli distribution, because you have learned about Bernoulli distribution. You see, okay, Bernoulli distribution and this classification, they are almost same problems, abstraction of same problem. And the second thing is you have to parameterize now. So I told you, you have distribution parameters, and then you have these model parameters. By using this model, you have to come up with these parameters. So in our case, we had this lambda. If you see, in this case, we had parameterized by lambda. You had to find that. So what I said, this lambda in the step 2 is equal to sigmoid of this. You will apply output on the sigmoid. So you parameterize by these models. So this is our distribution parameter, and this W was our model parameter. You parameterize basically this distribution with the model. So that's what the second step was. Parameterize the model, parameterize distribution using our model. Third step was define the loss. Now you have to define the loss. So how to define the loss now? I said, okay, loss should be defined somehow like this. You have certain example, like so x, y, y1 is the example. So you are saying that probability y given this x and w. Okay, this should be defined like this. Whatever probability you have used over here. Okay, and you got it from here, so you directly used it here. So you defined loss in this way. Okay, now you are applying a negative log likelihood. After applying negative log likelihood, you landed up at binary cross entropy loss. So this is what we also saw when we were defining entropy. So the amazing thing, the thing that you should be amazed at, is that we started with entropy. Okay, we started with basically information content, entropy, and we landed up at binary cross entropy, and we landed up at, let's suppose, categorical cross entropy, or in general cross entropy, something of that sort. And then we took KL divergence. We again landed up at this entropy. Somehow it was related. Then we saw probability. We again landed up at this concept that we can come up with this binary cross entropy. If you again use this algorithm, let's suppose for this categorical distribution, if you use it for categorical, let's suppose classification, where you have multi-class classification, you will use categorical distribution for that. And that distribution is again some properties. You will again use the same thing. You know, you will come to categorical cross-entropy loss. You will find that everything is boiling down to categorical cross-entropy loss. If you use some regression problem, if you have, so here this categorical distribution was used in terms of multi-class classification. Multi-class classification. And you landed up as categorical cross-entropy loss. If you have a regression problem, if you have a regression problem, so what you can do is you can use Gaussian distribution. So if you use Gaussian distribution and follow the 4 steps that I told you, step 1, choose a distribution, and after that model the parameters of this distribution by using the model. So you have to parameterize this by using the model parameters, and you choose this Gaussian distribution, you will land at mean squared error loss. So this is what you will do. So after you choose the equation, then you construct a loss function, and then you apply negative log likelihood on that, and you will come to all these loss functions by using these things. Okay, I hope that everything is clear. So I'll stop this recording now, and I'll take your questions if you have any.